Okay, guys, going on to organic lesson number 2. We're talking about organic drawing of some organic compounds and some hydrocarbons. And we look at some general ideas and notes about these compounds, and then get into drawing some of the naming on some of these. So, just take a look at the concept of saturation. So, when we talk about saturation, usually when we talked about the solutions unit, we looked at the fact that when you add enough solute to a solvent, you add to the point where you can't add any more, and no more will dissolve. We use that saturation. If you take a sponge and you add a lot of water to it where it can't sop up any more water, then you could say the sponges or a towel would be saturated, it would be filled up. So we use the same idea when we talk about these carbon compounds. So when compounds that are all carbonyls are separated by only single bonds, then we can put the maximum amount of hydrogens around those carbon compounds. So we're going to call that something that's saturated. So when you have all single bonds and those carbons are filled up with hydrogens on each one of their single bonds, then we're going to call that a saturated hydrocarbon. Okay, if carbon atoms in a compound have at least one double or triple bond, then we have an unsaturated carbon compound. So we're going to have to just watch what that is. So for example, a good example is something called some saturated fat. So saturated fat and unsaturated fats are two types of things we heard in food science. A saturated fat, one called lauric acid, and this is the main acid or fatty acid that's in coconut oil. Okay, and that has 12 carbons long. You can see this long chain of 12 carbons, and it's got its COO at the end, the fatty acid part at the end. Okay, that's why it's called a fatty acid. It's got a long chain. Okay, and what's not important is really the end of this chain. It's really the chain itself. That the chain has all single bonds. If you look, all of these carbons have single bonds in them. Okay, so that would be a saturated fat. If you look at linoleic acid, which is in sunflower oil, so 66% of sunflower oil is actually this linoleic acid. That would be an unsaturated fat. You can see that we have double bonds present in this area and this area of this chain. So it's a much longer chain with the same type of fatty acid at the end. However, it's got areas in the chain where there's some double bonds. So we're going to call that an unsaturated fat, or sometimes they even call this a polyunsaturated fat because you have more than one area for the double bonds. All right, and that's it. Most saturated fats, because they have the maximum of hydrogens, are going to be solid at room temperature, and many times unsaturated fats will be liquids at room temperature. Okay, so the question becomes, what kind of things generally are saturated? And the fact that we look at the term alkanes, the question is, are alkanes saturated hydrocarbons? Okay, and the answer is going to be yes, because alkanes have all single bonds between the carbons. So if you have all single bonds, then you can fix the maximum of H's between carbon atoms. Okay, really important. Okay, and then propene, is that saturated or unsaturated? Well, if we look at propene, propene is 3 carbons separated by your single bond. So C, C, and C. And ene means double bond, so we're going to have a double bond in there. So that is an unsaturated hydrocarbon. Okay, so important to know unsaturated, saturated. So overall, saturated means you have all single bonds. Unsaturated means you have doubles or triples. Okay. Next thing, we talk about the types of formulas. When we want to represent these, there's a variety of ways that we can represent these organic formulas. Number one, okay, there's due to a huge number of them. Really, there's general 3 ways we could do this. Okay, and each way has its own use depending on what you want to use it for. So number one is something called the structural formula. When you draw a structural formula, basically drawing the molecule out with its bonds and everything that's attached to it. Okay, it gives you the maximum detail, but it's very bulky to draw, not easy to text, not easy to email, not easy to communicate, with a computer. But it does give you everything you need to know about the molecule. So, example, if I was going to draw butane, I was going to draw butane as but, meaning 4 carbons, ane single bonds. So I would draw butane as, I'll draw it here, C, C, C to C with my 4 H's around. Again, if you tried to text this to somebody, you'd probably go crazy. So we're going to go H, 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 H is here, 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 and then you have butane. All right, so that would make sense. So that would be a structural formula. Why is it good? It gives you maximum detail. Why is it bad? Very bulky, very tough, time consuming, takes a lot of paper, takes a lot of space. Okay. Number two is something called a condensed structural formula. This is a basic structure, but without the bonds, and it's space saving. Okay, and these are very popular, and there's different types of ways you can have a condensed structural formula. But basically, what we're going to do is go carbon by carbon and write down what is on the chain. So, for example, if I wanted to do this for butane again, I'm going to use butane. I'll use what's above this. I'm going to say CH3. So I'm going to take carbon number 1 here, CH3, and then CH2. Okay, and then next is a CH2. So I'm just going to simply go carbon by carbon, and then lastly CH3. Okay. So you could see this is definitely more concise, but it still gives you the idea of the chain in a row. It still tells you what's attached to each one, but it breaks out. These are very, very common. You can even send this like this. You can even say CH3, sometimes dash CH2, sometimes dash CH2, sometimes dash CH3. Okay, again, different types of ways that you could show this. Sometimes they can do a mashup of both. It depends on the way you do it. So either one of these is correct. Either one is acceptable. Okay, very common. Condensed structures are very common. Really has the best of both worlds. Okay, and then lastly is something called the molecular formula, and this is your friendly neighborhood molecular formula like you've seen all the time. Simply, you just group all the elements together into a compact formula. Again, this is quick and easy. You can put these in reactions. Again, the structural and condensed structural, if you put that in a reaction, if you had to balance a reaction, that probably wouldn't be great, but molecular formulas are great for this, and it's even great for GFMs, but it lacks detail. So it really doesn't tell you how the thing is built or how it's put together. So for example, I just put it all together, and if I said butane, I would just say C4H10. Like how is that really telling me the structure? Okay, so this doesn't really tell me anything about the structure. If I gave you C4H10, how would you actually build that? How would you actually draw that? Now, of course, I told you because it's up here. But if I just gave you this with a blank piece of paper, how would you actually draw that? You'd have to do it by trial and error until you got it right. All right, so these are really, you'll see all three types of these formulas, and it depends on what you want to, what they ask you to draw. You have to be able to know how to do that. All right, so structural, condensed structural means shortened, and then your molecular formula. Okay. All right, and last but not least, some of this extra information before we start naming is really something called an isomer, and the prefix meaning isomer. Prefix meaning iso means same. Okay, and the word mer means piece, pieces or pieces. All right, so same pieces, which means if I gave you suppose I gave you 5 black Legos and 5 red Legos, and I asked you to build something, and you built a little bridge out of it, and then you gave it to me, and I built like a little tower out of that. Well, you would build a bridge, I would build a tower out of the same 10 Legos, but the structures will be different. All right, we'd have totally different structures. And maybe if you gave it to someone else, they would try to build a little chair or something out of that. So if you have a certain amount and you build different structures out of that, you still use the same amount of elements, then that's called a isomer. All right, so organic compounds become larger, more complex. The ability to connect different ways increases. Compounds that have formula have the same formula, so same stuff, but different structures are called isomers. Okay, and you might say, well, what's the big deal if you have the same stuff if you build it differently? Well, if you build it differently, you're going to have different chemical and physical properties. Okay, isomers must have the same number of each element in their formulas. Many have vastly different properties, chemical and physical properties. They can smell differently. They can react differently. They can be of different potencies. They can be poisonous. They can be safe. So you really have to watch this. And a really fun fact, C20H42 is a molecule, has 20 carbons and 42 hydrogens. There are literally 366,319 different ways to connect C20 and H42. If you go to 40 carbons and 82 hydrogens, there's this. I think that's 62 trillion. Yeah, that's 62 trillion different ways, 62.5 trillion ways that you can connect 40 carbons if you wanted to sit there and do it. All right, so the amount of possible structures that you can draw in organic chemistry is staggering, especially when you have a lot of atoms. All right, so if you want to draw 2 isomers of butane, simple. Well, as you could say, butane is 4 carbon single bonds. Okay, I could say, okay, if I'm going to draw butane, very simple, I could say, okay, carbon, 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 carbon. 4 in a row sounds good to me. So I can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So that would be C4H10. Sounds great. Now, however, if you look at this, you'll see 4 in a row. Is there another way to connect these? Okay, and if you do that, you can also connect it in a different way. Okay, and please don't do this. You can't connect it like that. Okay, and you can't connect it. Okay, this is a no. Okay, and this is a no. So that's no, and you can't connect it like this either because this is still carbons in a line. How can you connect them so they're not a straight line? That's a straight line. That's consecutive, 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 consecutive. So this also is a no. Nice try. Okay. The only other way you can do this, and there's only two ways. This is the first way. Number one is the first way. The only other way you could do this is go 1, 2, 3, like that, and then put 1 off the middle. And that is my yes. Okay, so this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is the only other way you can do this, and you can't call it butane because this is butane. This has to be something different. So we're going to call this methyl, and we'll see why later we're going to do this. We're going to call this methyl propane. Okay, so this is a different structure, and guess what its formula is? C4H10. Okay, so again, a lot of this is trial by error, guys. A lot of this is trying out something differently. All right, so this is called a branched chain. This is called a chain, straight chain. This is called a straight chain with a branch on it. It's got a carbon branch. All right, so this is not. This is an isomer. So these are called isomers of butane or isomers of C4H10. Okay, another way you could do this is, let's just say we had an O in there, and again, O is going to form double bonds. Just a fun way to do this. We can say C, 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 and we can say, okay, well, I have 3 C's here, okay, and that would be 6, but I got to fit the oxygen on here. So that would be 1, 2, 3, 4, 5, and then we can go like that, and we can form an alcohol. We can take that. I'm not going to name this right now, okay? Or I can actually do this. I can actually split this. I could take the oxygen and move them to the middle, and I can do this. I can take oxygen as an oxygen bridge between the carbons and put 3 on each end carbon. So either way, if you check these formulas, I would have C2, there's the 2 C's, H1O, and 6 hydrogens, okay, on either one of these. So these would be 2 isomers of C2H6O. Now the question is, like if I just gave you this formula, which one would I draw? Well, you could draw either one. I would have to give you a different name, okay? So that's how that works. All right, so cool, that's what an isomer is. Again, isomers are gonna have same elements, different structures. You draw them differently. All right, moving on. Next thing, last thing is how we actually name these things. How we're going to actually name these things is a little bit of a practice, and this is going to be the last thing we're going to do. Okay, so what we're going to do is use our prefix and our suffix tables. The prefix is the number of carbons. The suffix is whether you have an alkane, alkene, or alkyne. Okay, just to double check, remember that your alkane, your ane is going to have a single bond. Your ene is going to have a double bond. That should be a double bond here. Okay, and ine is going to be a triple bond. So a single, double, triple. Okay, so this is a double bond here, single bond there, triple bond there. Okay, important to know, and you have your prefixes. So the most important thing, let's do this. Okay, seems like a lot of rules here, but it's not a big deal. Number one, find the number of carbons in the longest carbon chain. You have to find that trunk of the tree, that skeleton, that carbon skeleton, where you have the longest carbon chain. Isolate that chain, okay, and find that longest carbon chain, and find the number of carbons, and that becomes your prefix, okay? Number two, use table Q and note if there is any single, double, or triple bonds between the carbon atoms. Okay, it's important to know whether you have an ane, an ene, or an ine in the chain, okay? All right, and then what you're going to do is number those carbons starting from the functional group, and we'll talk about functional groups a little bit later maybe, okay? And you want to number closest to the functional group or the multiple bond. Okay, you want to locate any carbon branches. And any branch that hangs off the chain is going to be use a YL ending. Okay, so you're going to name those branches. Again, so a branch, think about a tree. A tree grows like this. The main carbon trunk is the tree. And then you always have little branches on a tree, right? Branches hanging off the tree. So you're going to name the trunk of the tree, the longest carbon chain, and then name the branches. The branch gets the YL. We'll see this in a minute. Okay, you're going to use numbers or use an address. Sometimes they use a carbon address or a number to show on which carbon on the address, on the carbon chain, the multiple bond or functional group is attached to. So you have to tell me on that chain where it is. Okay, and then table R is your group of functional groups, your alcohols, your ketones, your aldehydes, your acids. Okay, you're going to find out where they are on the chain also and adjust the name. Okay, and if there's multiple branches, you're going to use di, tri, tetra for multiple groups on the longest carbon chain. Okay, I know this is a lot of rules. Again, you're not going to have to memorize all this. You'll actually get it as we practice. So let's practice a little bit of this as we go through the rules. So for example, what if I wanted to draw 2,2? Okay, I wanted to draw 2,2 dimethyl pentane. Okay, and I want to provide the condensed and molecular formulas too. Okay, now anatomy of a name of a compound. Number one, the ending is always the longest chain. So that's the longest part of the chain. That's the longest chain here. Okay, and the branches will always be here. The branches will always be in front. Okay, and the address will always be in front of that. One way to put it. Okay, so you have your longest chain, your branches, and your address. So I'm going to draw this first. I'm going to say pentane. Well, pentane is simply 5 carbons. 1, 2, 3, 4, and 5. Separated by single bonds, and I got my chain. Okay, now you'll see dimethyl. Now di means 2. Methyl means 1 carbon. Remember, a meth means 1 carbon. And if I take meth and I take methyl and I put that at the end, that equals a 1 carbon branch off this chain. Now there's plenty of places I could put this, right? I could put I could put another carbon anywhere. However, and again, there's 2 of them. It says dimethyl, so there's 2 carbons. So what I'm going to do is it tells me exactly where to put them. It tells them to put them on carbon number 2. So where's carbon number 2? I'm going to name them. I'm going to say, okay, this is carbon number 1, this is carbon number 2, this is carbon number 3, carbon number 4, and carbon number 5. Okay, so I'm going to put a carbon branch, 1 carbon branch here, and the other carbon branch there. So that was my 2,2 dimethyl 2 1 carbon branches on that. I'm going to fill it with hydrogens. So I'm just going to use lines for my hydrogens here. A little shortcut. You have to put the hydrogens in. So H, 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 H all the way around here. Okay, and I will. That is my structural formula. So I'll just do it. H, 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 H. So I'll put all the H's around just because it's important to do and do it right. So we put all our H's around, and that's fine. All right, so I'm going to have 5 C's plus. I'm going to have C7. Okay, I'll have 7 C's. Okay, and I have to count my H's. So I'm going to go 1, 2, 3. I'll start with this carbon. So carbon number 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. C7, H16. That's what I got. Okay. Now, the condensed structural is simply going element by element. So to do that, I'm going to start with carbon number 1 is a CH3. Now, carbon number 2 is going to be interesting. Carbon number 2 is C. But to show that you have 2 1 carbon branches is I'm going to open this up. I'm going to say CH3, but there's 2 of them. So I'm going to close my parentheses 2. Okay. Then I'm going to say CH2. Then I'm going to say CH2. And then I'm going to say CH3. All right. And that's going to be my, so CH3, C, CH3 2 times 2, CH2, CH2, CH3. All right, now in this one, in trimethylhexane, now I have hexane. So that's my longest carbon chain. Okay, so I'm going to go 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. I have carbon 1, 2, 3. So I'm going to call that carbon 1, 2, and 3. And I have trimethyl. So I have 3 1 carbon branch. That's a 1 carbon branch. It's a 1C. Okay, but there's 3 of them. And where are they? 1, 2, 3. So I'm going to put 1 on 1, 1 on 2, and 1 on 3. Now you could put these also pointing down. You can put them up or down if you want to. You can put 2 up, 1 down, 2 up, however you want to do that. No big deal. All right. So that's my chain right now. So I have 6 carbons, 7, 8, 9. So I have C9. Okay, and then I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. All right, so I have C9H20. That is that. Okay, and then I would do my condensed structural as CH2, okay, parentheses CH3. Remember, you want to show that that is attached to it. Same thing here, CH2, well, actually, it should say CH, CH3, okay, and then the same thing, CH, CH3, okay, now I'm here, CH2, CH2, CH3, okay, just in case you want to see the condensed structural. All right, so I think this is easy because you're drawing the structure from the name and it's telling you the directions. Now you have to go from the structure back to the name. So now I'm going to find my longest carbon chain. Let's find it. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's 8 carbons in a row. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to call that the name is going to be octane. That's my longest chain. Okay. Now, what I've done right now is I've named the longest carbon chain. And I do have a branch. And this branch is a 1 carbon branch. So we're going to call that meth is for 1 carbon. Branch means YL. So that's a methyl. Okay. Now, I do have a triple bond in here too. So I'm going to have to change the name of this to not octane, but octine. Okay. And the problem is that we have to say where that is because this triple bond could be anywhere in the chain. And this is also hanging off a different carbon. So we're going to have to tell people where this is. Again, this is a long block of carbons. So what we're going to do is we're going to number from the end that produces the lowest number where the triple bond is. Let me repeat that. We're going to number from the end that produces the lower numbered carbon in the chain, in the address. So watch this. I'm going to number 1, 2, 3, 4, 5, 6, 7, 8. And I'm also going to number from the other end to see. 1, 2, 3, 4, 5, 6, 7, and 8. Okay? Now, what I'm going to do is take a look at the numbers where I numbered. And I'm going to choose the number that's the smallest. And that's going to be the number I'm going to use for the address of that carbon. So you can see right here is where the triple bond is between these 2 elements. Is it 6? Is it 5 between 5 and 6 or between 3 and 4? And I find that 3 and 4 produces the lowest numbers. So I'm going to choose this to be 3-octine. That's the name of this main chain, 3-octine. Now, because I chose to go this way and name this 3, that would make this 4, 5, 6, 7, 8. And now on carbon 7 is this methyl. So I'm going to call this 7-methyl 3-octine. And that is the name of that structure. Okay, so again, a little complicated, a little bit, it takes a little getting used to. The key is finding the longest carbon chain, right? The longest carbon chain is the way that it is. So again, find the longest carbon chain, name it. See if there's a double bond, triple bond, single bond, name that chain, get that chain figured out. Know where the double bond or triple is, name it according to the smallest address. Again, these numbers are addresses. They're like driving directions, like numbers on a block. All right, and then find your branches, put them in the front, add those numbers, and you are good to go. Okay, just make sure you practice. All right, have a great day.